Let's take a little side tour and let's look at the conditioning of the linear least squares problem. Okay, remember, conditioning had to do with how sensitive the solution is to a small change in the right hand side. Now, in terms of the linear least squares problem, what does that mean? Well, we're looking for x hat that minimizes this right here. And what we now want to do is say, well, what happens if we make a minor change to the right-hand side vector b? Let's call that delta b. And remember, we're having the delta and the b touched to indicate that this is a whole vector of small changes. Okay. What we then get is a change in the solution. Okay. Well, let's go over here. What does that really mean? Well, let's say that this yellow here represents the column space of A. What we have is our vector B, which typically will not be in the column space of A. And what we saw before was, to solve it, we looked at the projection of B onto the column space of A, and then we found the X that takes the correct linear combinations of the matrix A to give us b hat. Right? So, b hat then is equal to A times x hat. What happens if we make a small perturbation? What happens if we change it slightly? Well, then we end up adding a small change to b. And what that means is that there is also a small change in the projection of b plus delta b. But because projection is multiplication by the projection matrix, what it means is that we can look at the projection of b hat, and the projection of delta b, let's call it delta b hat. And the projection of b plus delta b is then the b hat plus delta b hat. Not sure if that hat is coming out so well there. Alright? So that gives us this vector right here. And then what we're looking for is the x hat plus delta x hat that satisfy, let's see, b hat plus delta b hat. Got it? Alright, so that's what we have written down right here. And just like when we looked at the conditioning of matrix A, or of the linear system AX equals B, solving that linear system, we can take this and subtract off that to get this right here. Alright? Now you can imagine that the angle between B and the column space of A is important, because if B was almost orthogonal to the column space of A, then B could be very large, delta B could be relatively small, but the change in the solution could be very large. So somehow this angle between B and the column space of A, we would expect to come into the picture. So let's call this right here, that angle, theta. Okay? And we then know that the cosine of theta is this distance divided by that distance. Since we're talking about the cosine now, we need to talk about the 2 norm, because we really are talking about Euclidean length when we talk about the cosine. So we get that the cosine of theta is equal to the 2 norm of b hat divided by the 2 norm of b. And what that means is that the cosine of theta times the 2 norm of b is equal to the 2 norm of b hat. Now, b hat was equal to A times x hat, and we know that the 2 norm is a consistent matrix norm and therefore a submultiplicative, and therefore this is equal to the 2 norm of A times the 2 norm of x hat. And then this right here we know is equal to the largest singular value of matrix A, sigma sub 0. Okay. And if we manipulate this a little bit, what we get is that 1 divided by the solution vector x hat, whoops, this here should have been a less than or equal to, right? Not necessarily an equal to. So 1 divided by x hat in 2 norm then is less than or equal to, and now we can take this to the other side, and what we get is sigma 0 divided by the cosine of theta times 1 over the 2 norm of b. Now when we just looked at solving a linear system where we know there was a solution that looked like this right here, that cosine did not come into play. Why? Because the column space of A is the entire space, and therefore the angle between any vector B and the entire space is clearly 0, because that vector is in that space. You got it? Okay, so now that we have worked this out, let's turn to this equation right here. All right? Now, we can rewrite that as A times delta chi hat, the change in the solution, is equal to the projected change in the right hand side. And then because delta b hat is in the column space of A, this right here actually means that the change in the solution is equal to the pseudo-inverse of A times the change in the right hand side after projection. This right here, remember, is equal to A Hermitian A inverse times A Hermitian. And all along we're continuing to assume that the columns of A are linearly independent. And once we have that, we can take the 2 norm of both sides. And then we can use the fact that the 2 norm is submultiplicative to find out that that's less than or equal to the pseudo norm of A in 2 norm times the times the 2 norm of the change in the right hand side after projection. And then we have a little homework in which you determine that this here is equal to 1 over the smallest singular value of A, sigma n minus 1. And if we put all of that together with what we did right here, we know that this times this must be less than or equal to this times that, because all these quantities are positive. So what does that mean? That means we come up with that the change in the solution relative to the size of the solution, all in 2 norm, is bounded by sigma 0 divided by the cosine of theta times, we should say 1 divided by the cosine of theta times sigma 0 and then divided by sigma n minus 1 times the change in B after projection divided by the change in B, all in 2 norm. Now that's not quite what we want. What we really want is the relative change in B, which means we want delta B divided by B. How can we get there? Well, we can multiply by 1. And then this divided by this is exactly the relative change in the right hand side. And then this divided by that looks suspiciously like this divided by that, doesn't it? So what it really is the cosine of the angle between the change in the right hand side and the column space of A. How can we summarize all of that? Well, if you think about it carefully, what that means is that we end up with the change in the the change in the solution of the linear least squares problem. This should have had a hat on it. There was a hat on that. Is bounded by the cosine of the angle between the change in B and its projection, or the column space of A. Let's call that angle theta hat, divided by the cosine of theta times sigma 0 divided by sigma n minus 1 times the change in the right hand side. Everything in 2 norm. Right? And then you can say, well, wait a minute, we can't really control where the error points, the error in the right hand side. And therefore we probably should be pessimistic and look at what the maximum of cosine theta hat is. But cosine is bounded by 1. So at worst, you can say, well, that's less than or equal to 1 divided by the cosine of theta times sigma 0 over sigma n minus 1 times the change in B over B. Now, cosine theta is determined by the actual right-hand side, so that needs to stay. And this then tells you by how much a change in the right-hand side can be amplified into a change in the solution of the linear least squares problem. Right? Now, you may want to think through, what happens if the cosine of theta is 0? What does that mean in that picture? What happens if the cosine theta hat is 0? Wait a minute, cosine theta hat is 0, then you're telling me that a change in the right-hand side has no effect on the solution at all. What does that mean? Think about it.